Welcome to Emergent Behaviors channel. Today we are diving into a bold idea. What if we stop treating a large language model as frozen at test time and instead let it update its weights while it solves the problem? This approach comes from Gonal et al. 2026 with a powerhouse mix of Stanford, NVIDIA, UC San Diego, and Together AI behind it. In this video, we will unpack the problem with frozen LLMs, what TTT-Discover is, the two secret weapons that make it work, and the results across math, kernels, coding, and even biology. Let us get into it. Now, look at this phrase, frozen brain problem. Notice what it's claiming. Standard LLMs are frozen at test time. That means when you ask it a question, fail, ask again, fail again, nothing inside the model actually changes. Even with test time compute like best of n, you're just sampling more guesses and picking the least bad one. Make that 9999 failures vivid. Imagine failing the same puzzle 10,000 times, but your brain wipes itself after every attempt. You do not learn the trick. You just roll the dice again from the same distribution. Why does this matter? Because more samples is not the same as accumulating experience. So, if we compare this with our AKA human thinking, after discovering a failure, the first reaction would be, wait, that approach was wrong. Aha, I need to update my synapses. Notice what it's really saying. Humans do not just flip through the same book harder. When we hit a dead end, we change the way we think. And that's the punchline on the slide. Sometimes the answer is not in the training data, not in the book at all. So, discovery is not just search, it's adaptation to the specific problem in front of you. Why does this matter for AI? If we want an AI to actually discover, it needs a way to turn its own attempts, especially failures, into learning signals. Enter TTT. Instead of keeping the model frozen at test time, TTT-Discover actually runs reinforcement learning during the test. Notice how they approach the test problem itself. It is no longer just a question to answer. It becomes the environment the model interacts with. Each attempt is like an action, and the evaluation is the feedback loop. What is interesting here is how that flips the out-of-distribution problem. Rather than treating it as, we have never seen this, good luck, they turn it into the new training distribution right on the spot. And the goal is very specific. Continual learning aimed at one exceptional solution, not general purpose improvement. The model is training itself as it goes. In this graph comparison, on the left, standard RL is basically trained to maximize average reward. Notice how that pushes LLM toward the high average zone. Safe, consistent, and honestly, boring. LLM gets steady 3s, but they rarely get a 10. On the right, the TTT-Discover framing flips the scoreboard. You see attempt after attempt labeled garbage, 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 and then suddenly, Nobel Prize. What's interesting here is that discovery looks terrible on average until it doesn't. Have you ever wondered why so many great labs tolerate failure? Because scientific discovery doesn't care about the average. We should optimize for the outlier. Chase the maximum reward, not the mean. So how did they do it? Here is secret weapon number 1. It is all about bending the loss function so the model stops caring about the average attempt and starts chasing the rare win. Notice how they approached it. They aggressively favor the best outcomes and basically ignore the rest. Why does that matter? Because in discovery problems, the breakthrough is an outlier, not the mean. And that adaptive beta line is the key. Beta is a risk factor knob. If the model is playing it too safe, you turn beta up and suddenly high reward, risky attempts dominate the learning signal. Remember, when we discussed previously maximize the outlier, this is the mechanism that turns that idea into actual training. Secret weapon number 2. Why walk the first 5 miles again? That is the whole idea of state reuse. Instead of restarting every attempt from scratch, we keep the progress that already got us somewhere. Notice how they approach the solution space. We save promising states, like partial code, half-finished proofs, or a setup that almost worked, and drop them into a buffer. Then, when we do the next rollout, we do not begin at zero. We pick up from one of those saved checkpoints. What's interesting here is the prioritization. We keep exploring paths that have ever produced greatness, even if the overall attempt was inconsistent. Why does this matter? Because breakthroughs often come from messy drafts. Finally, the TTT loop. The model does not just answer once and hope, it cycles. First, it generates a big batch of rollouts, basically many different attempts at a solution. Then, those attempts get evaluated with a real scoring function. The best signals feed back into training. The model updates its weights, and the whole process repeats. Notice the concrete knobs, 50 training steps, and 512 rollouts per step. That is structured compute. You are buying breadth of exploration and then turning it into learning. And the cost callout matters, about $500 per problem. Why spend that? Because you are paying for targeted improvement, not just more guessing. Quick side note, if you want to dive deeper into TTT math, please ask in the comments. For math results number 1, look at this comparison. The old state-of-the-art from AlphaEvolve sits at 0.380924, and TTT-Discover nudges it down to 0.380876. That looks tiny, but in a hardened math benchmark like the Erdos minimum overlap problem, shaving off even that much is a real breakthrough. Notice how the slide calls the previous approach so polite, so symmetric, meaning it stayed in neat, human-comfortable patterns. What's interesting here is the new best result is described as ugly but effective because it's asymmetric. Why does that matter? It hints TTT explored regions people tend to avoid, and it did it with a 600-piece asymmetric construction. Math result number 2. Look at this bound. This is where the method proves it is not just doing clever search. The previous best result from Theta Evolve had C1 less than or equal to 1.50314. TTT-Discover pushes that down to C1 less than or equal to 1.50286, which makes it the new state of the art. What's interesting here is how they got it. They did not start by polishing the best-known certificate. They started from scratch and still beat approaches that were literally fine-tuning existing winners. Why does this matter? Because test-time learning means the model is not just remixing known answers, it is actually building a better one during the attempt. For engineering result, look at this head-to-head on the H100. The best human TriMul kernel clocks in at 13,001 microseconds, and TTT-Discover drops that to 11,000 markiscuties. That is about a 15% speed up, not a rounding error, a real win. Notice the lane view. Those stacked lanes are basically a performance profile of what the GPU is actually doing over time. So, we are not talking about theoretical flops. We are seeing real kernel behavior and where time is spent. What is interesting here is the mechanism. The model fused operations so it could cut overhead, and it confidently used reduced precision FP16 in spots where humans were too cautious. Why does this matter? Because these small choices compound into big runtime gains. For competitive coding, on the @coder side, notice the claim is not just pretty good. Their approach was strong enough that, if submitted, it would have placed first in 2 heuristic contests, AHC039, the phishing problem, and AHC058, the Apple economy. Why does that matter? Because those contests reward clever, domain-specific scoring tricks. For biology domains, what's interesting here is the result uses a totally different reward, denoising single-cell RNA-seq. They report better denoising than magic, measured by improved mean-squared error. Same test-time training loop, wildly different target. That's the magic of TTL. Here are the ablations done by researchers. They are basically asking, do we really need the fancy stuff? You have 3 lanes to compare: standard RL only, reuse only, and the full TTT-Discover setup. Notice how they approach the simplest baseline first. With no test time training, the run just stagnates. It is not that it is slightly worse, it stops getting meaningfully better. What is interesting here is the other failure mode. If you remove the entropic, risk-taking objective, improvements still happen, but they are painfully slow, so the takeaway is blunt. You need both ingredients, deep exploration through reuse, and the objective that rewards bold jumps. Okay, notice how they approach the efficiency question. They used an open-source model, GPT-OS120B. That matters because it means the method is reproducible and inspectable, not just, trust us, it worked. What's interesting here is the price tag. Only approximately $500 of compute per problem. Not per month, not per training run, per problem attempt to chase near state-of-the-art results. Have you ever wondered why some teams get breakthroughs without massive clusters? The key insight here is the takeaway on the slide. You don't need a supercomputer. You need a smarter process that turns each attempt into learning. To wrap up learning to discover at test time, here are the 3 big takeaways. First, do not just search. Learn by actually updating the weights during the run. Second, for discovery, average is bad and max is good. You want to maximize the outlier that reveals something new. Third, open models plus test time training can be dangerously good. This is the shift from prompting harder to adapting in the moment. A huge thank you to the authors for their amazing research. Thanks again for watching so far. If you want to read more, our detailed blog post, complete with slide deck, quiz, and flashcards, is available at emergentbehaviors.com and linked in the description. Let me know your thoughts in the comments. What domain would you try TTT-Discover on first? Thank you for your time, and I'll see you in the next video. Bye!